Hello and welcome back to Calculus 1, section 3.3, Rules of Differentiation. Remember how you had to go through the limit procedure to find the limit, to find the derivative? No?
Like we just did?
Yeah, like we just did, exactly. So we're going to go away from that. What we are going to do is we are going to come up with shortcuts and memorize them because it's easier. So you did this in life before, so it's not going to be anything new. Instead of going 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15, you memorize 3 times 5 is 15. And you made your peace with that. Otherwise, you would have to sit there and go 3 plus 3 plus 3, right? The next time you did this was with exponents where 2 cubed was 8, because you memorized that. Rather than 2 times 2 is 4 times 2 is 8. And now, you are going to make the peace with the fact that the derivative of x squared is 2x, because you're going to memorize that. But the cool thing here is that you are memorizing formulas, and then we're going to build upon those. So we start by memorizing that the derivative of a constant is 0. Now, when you are looking at the statement in English and a statement in mathematics, there has to be one-to-one correspondence. This thing over here is called differential operator. And that is the instruction given to you what to do. Differentiate constant, and you get 0. It's the set of instructions, like license and registration. You're familiar with that one, right? Very good. So this is the same thing, except you don't have to pay money. So this d dx. Now also observe the words. It says of. Of means multiplication. So there is a times over here which we don't write. The differential operator operates on whatever is in these brackets and changes it. Now, you've seen this earlier with something that it's called mathematical operation. You have operation operate on 2 numbers and change them. So 3 plus 8 is 11. If I change the symbol, the result will change. Well, now you are moving a step higher. You are not operating on the numbers, which are operations. You are operating on functions, and those guys are called operators. You've seen the limit, and now you see the derivative, and you will see the integral. So those are the almighty 3. 3 operators that change functions. We know that we can add 2 functions and get a new function, right? But now, these guys, operators change functions. So now, when you have a constant here, the derivative of a constant is 0. Why? Why is the derivative of constant 0?
Math says so.
Math said so. Great.
This is going to be a straight line. So
Going to be straight line, so?
no line that can be touching like a tangent or something like that.
Well, every tangent line is a straight line. Why is the derivative of constant 0? Okay, so horizontal line has 0 slope. Good. Is there an easier answer? What is the derivative? What is the purpose of the derivative? What does it do? Yes? To write the rate of change. What's a change in a constant? What's a change in a constant? 0. Constants don't change, hence constant, right? So, the derivatives measure the change. Constants do not change. The derivative of constant, common sense, must be 0. We can actually do the proof for this using our limit procedure. For every single formula that I write now and in the future, you can go and prove it. H goes to 0, and then you have C minus C over H, right? And that's 0. Yay! All right, let's take a look at the next one that you have to, well, let me give you an example here, or two. What is the derivative of 7? 0. What's the derivative of pi? 0. Good. Enough examples. The next one is the derivative of anything polynomial-like, x to some exponent n, is going to be n x to the n minus 1. Well, this covers a wide variety of problems. Square root of x is on the pile. 10th root of x is on the pile. But it also 1 over x to the 5 is on the pile, along with x to the 7 and all the other ones. So what's the derivative of x cubed? What's the derivative of x cubed? 3. What's the first step? Yes. Very good. Mr. Stark. Of Stark Industries. Or that's a wrong Stark.
Wrong Stark.
Oh, okay. Yeah, I think they ran out of names, so that's why. Because if that was the Stark, they would never be able to chop off his head. Because the axe can't go through the, right? Yeah, it's like grenades can't do anything to it. Can just simple axe or sword. So much better Stark, right? Much more power.
America kicked his ass.
It's the movie nonsense, okay? Yeah, you put Captain America against Iron Man, it's just gonna flatten him like a pancake. The same thing, the debate about the Batman and Superman. It's like, do you even debate that? It would squish him like a worm if you wanted to. It was like flick him. That's all he did. This all would take. If they existed, Superman would just need to flick him. That's it. Flick through the armor.
Beat the Hulk in the comics.
Yeah, that's why they call comics. They're comical,
So
okay?
nothing bad is said.
They're comical at best. All right? Just, it's on the stream, and I'll sign this. All right? I'll sign this anytime. Give me a break. Captain America against Iron Man is just a joke. All right, next one. What now? Oh, but it's the square root. Beautiful. See? So you have to get used to the fact that the formula accommodates more than meets the eye. Which one is that one now? No?
transform.
There we go.
Took me a second.
Hiding in the plain sight. Good. All right, perfect. So this one formula, try to fit everything, there we go. This one formula takes care of all of these cases. When you have polynomial looking term, x cubed, then you have a rational one, and radical. All of these guys are taken care by the same formula. Now, they will revisit this in the book a few times, change n into p, make sure that, you know, you can use whole numbers first, then you can use the rational numbers and then real numbers. You can use any number there as long as you can subtract one, and you can subtract one from anything, right? So that's that part. So now that you have these two rules, we are going to step away from taking derivatives and take a look at three rules of derivatives that are extremely important. Why? So this next rule says that you can take the derivative of the sum of two functions separately. So you take the derivative of one plus the derivative of the other. Now, this rule actually allows you to deal with the situation x squared plus 1. Remember we had x squared plus 1 in a first question today during the homework? So now we can take a look at the derivative of x squared plus 1. And we deal with it by figuring out the derivative of x squared separately from the derivative of 1. What's the derivative of x squared? And what's the derivative of 1? So the total is 2x, which is exactly what we had when I did the limit. Very first thing today, right? So this rule, now obviously you're not going to write this out, right, in the future. You will immediately go, oh yeah, it's 2x, and you're done. You don't have to write all the steps. As you go through this, it will become easier and easier. The next rule, I am not going to write it out again from scratch. I'm just going to go to the red one and put a minus sign there. See the minus signs? So two rules in one. It's like when you're buying packets of salmon on sale. Put this on a cloud. So, oh, you're allergic? Then buy 4. So you have addition and subtraction here. And the third rule says that if you have a constant multiplying the function, you can kick the constant in front of differentiation and just differentiate the function. So the derivative of c times f of x is c times the derivative of f of x. Now this will allow us to differentiate 5x cubed. Try differentiating 5x cubed. You know how to deal with x cubed from the previous formula, and now this rule above allows you to deal with 5x cubed. We'll do some spicier examples soon. Checking on the content. Are we okay with this? We're going to kick 5, and then we're going to differentiate x cubed. We will have 5 times 3x squared for total of 15x squared. Are you going to write all of these steps in the future? The answer is hell no. You're going to go 5 times 3 is 15, right? You're just going to plow through this in your head, not even writing anything down. You're just going to say 5 times 3 is 15, x squared, done. But it's important for you to see the rule at the beginning to know that it's not, that it's actually a mathematical rule that we have to do that. Now, one that might create some confusion, especially after we do 3.4, is the derivative of 6x squared. It actually falls under the rule with a constant. We are going to learn something that is called Quotient Rule, and a bunch of people do the Quotient Rule for this, but hell no. There's no need. You can, but then you don't take a sledgehammer to put the painting on the wall, right? Take a smaller hammer. Or a mirror, like someone I know at home. Yeah, the base of a mirror. So what do we do? Perfect. What do we do? Exactly. So we kick 6 in front, the differentiation, and write 1 over x squared as negative x, and now we know that this becomes negative 12 x to the negative 3, which is negative 12 over x cubed. Meditate on this example. Right? So 6. And then we have x to the negative 2. Negative 2 drops down. Negative 2 times 6 is negative 12. And negative 2 minus 1 is negative 3. So if you're not getting these concepts, you must work very hard, because you will be taking these derivatives every day until the end of the calculus and differential equations and so on. This derivatives, so this lecture 3.3 is the central lecture of all of Calc 1 now. Because these are your shortcuts to take derivatives. You do not want to go and do the limit every time. I mean, maybe you do, and you like pain, I don't know, then you do the limit every time. Each one of these questions can be done with the limit. So we have all of those. And I would like to talk, yes?
So if you know how to do all the shortcuts, do you have to know how to do the limit?
The answer is no. Because the limit procedure is the definition, right? And, I mean, some people know it because they're cool, right? Once you know that 5 times 3 is 15, you actually don't want to go and say 5 plus 5 plus 5, or 3 plus 3 plus 3, right? Because you now know something faster. So the same thing goes with this. Fair?
So, if I get real good at this,
And you will.
it's okay that I wasn't good at the limits.
Yes.
Right.
But then there's chapter 8 and 9 in Calc 2, so
We'll cross that bridge when we...
I just did that.
No, but we're not there yet.
Well, don't worry about it. Time flies when you're having fun.
And in hell.
Yeah. Now I want to talk a little bit about notation, because I get to be highly allergic to certain things. Many of you seen -1 with the word notation next to it, that's when my allergies kick in. But then allergic reaction becomes more severe as we go through the semester. So writing limit equals 9 has no meaning in mathematics. That's nothing. Also writing VA equals -2 has no meaning. All of these are considered wrong answers, even though the limit of some function was 9 and the vertical asymptote was -2. These notations do not mean anything, and if you move out of your comfort zone, which is this class, no one would understand what you say. Because it doesn't make sense. It's not anything that we as a species agreed upon, and mathematics is the only universal language. Further, when we're talking about derivatives, you can write derivatives in line or start a new line. So I'm going to give you 2 examples. So this is notation, so that everyone understands what you're talking about. You can say f of x equals x to the 5. And then you can go to the next line and say the derivative is equal to 5x to the 4. So observe that you have a line for the function and a separate line for the derivative. This line is all about functions, and this line is all about derivative. Do we see clearly separated, right? Or you can say the derivative of x to the 5 is 5x to the 4. So this is the only way how you can put these guys together. The issue obviously is when you have f of x equals to x to the 5, and then you write equal 5x to the 4. You see the problem there, right? You say the derivative is equal to the function, and then you also say even crazier thing, which is x to the 4 is the same as x to the 5, which they're not. Not by far. They're both polynomials, but one is even, one is odd, for instance. And they have different amount of zeros, and behavior is different, and all of your PreCalc stuff, right, between those two is off. So if you want to write in line, you will use this notation. If you don't want to write in line, you will write separate lines, function, and so on. So I will sometimes use one, sometimes the other. I'll be switching between them. This one is derived from Newton's original notation. Newton's original notation for derivative, when he made this stuff, was y with a dot above that, which eventually grew into y prime, which grew into f of x prime as we improved the notation for all of these things throughout the years, right? Newton, 1666, right, with calculus. On the other side of the or, you have Leibniz. And Leibniz said dy dx. And that notation is far superior to what Newton has, but we will discover why as we go through the class. When I'm working with derivatives, I use this about 90% of the time because it's much better. But I will explain why and how later on. All of these guys, all of these are notation for derivatives. You are going to see in this course this one, this one, this one. If you go to differential equations, you are going to see derivative operator. So instead of writing d dx, you write capital D and then you put x to the 4th, right? Means the same thing. So you don't have to know that one now. There will be partial derivatives in Calculus 3. They look like this. Has this backwards d. You know, when the way you can make this is you write the ugly 2, and then you just, you know, and that's a partial derivative. All right, that's how you can get it. So partial derivatives aside, that's Calc 3. We are going to use these notations, and most of the time we're using Leibniz notation. Leibniz notation being the best, and I'll explain eventually throughout the course why Leibniz notation is the best. It's towards the end of this chapter. I believe 3.7 or 3.8 is when 3.9. It's one of those sections where I explain why is that one superior. So, reset. The derivative of a constant is 0 because there is no change. The derivative of x to the n is n, x to the n minus 1, and we have the whole spiel of different situations where we can use it. Then we jump into linearity rules. The first two rules, addition and subtraction, tells us that we can deal with each term separately, and the one on the bottom tells us that we can kick the constant in front of the differentiation. And then I jumped and I talked about notation, which is extremely important, so you all know the proper way to denote these things. And the last part, I believe, is the exponential function. They define a number e. Okay. Do they have anything else? Okay. So the last big formula, we still have to talk about higher order derivatives, but the last big formula is that the derivative of e to the x is e to the x. This is the only function that does this, obviously. Can't have more than one. So the derivative of e to the x is itself. Now this e is a special number, and that special number is defined as the limit when n goes to infinity of 1 plus 1 over n to the n. This is the calculus definition of number e. It's about 2.712821, no, sorry, 2.7182818284590, blah, blah, blah. That number is going, you used it a lot, you've seen it obviously in your pre-calculus course, but here is its definition in calculus, and we will use this limit a lot eventually, so you should remember this limit. So let's see. What's the derivative of the function f of x equals 5x squared plus 3 over x minus e to the x. What do you have? What should I write? I'm sorry? The answer, yes. What should I write as an answer?
Minus 3 over x.
There is something before 10x. Uh-huh. So f prime x equals to?
Minus 3 over x squared. Minus exponential x.
Good. We all have this? Perfect. Right. Yes.
Given then constant before e to the x, do we take like whatever the constant is times e to the x? So if it is like 5.
Yes, it has to follow the rule.
The constant rule, right?
We have the rule for that.
Okay.
Whatever this is, it doesn't matter. The rule says constant gets kicked out. Yes. What happened?
How did you get the middle term?
Oh, I didn't hit it.
How did you get it?
Oh, how did he did? Ask him. So you write this as 3 times x to the minus 1. And then the derivative of this is 3 times negative 1 x to the negative 2. And then put it together. Okay. Now, there is one problem that is going to be in every section of chapter 3. And that problem starts with find the equation of the tangent line. Entire chapter 3 is focused on figuring out different ways to take derivatives. We learned how to take the derivative using the limit, and that turned out to be labor intensive. Now we know how to find derivatives faster. That means that we can find slopes faster because we can find derivatives faster. So every section where we learn new methods for derivatives, whether it's implicit differentiation, chain rule, whatever, there will always be a problem that says find a tangent line, because you're taking derivatives of functions and functions have tangent lines. So find the tangent line to the function f of x equals e to the x at ln 3. What is the procedure for tangent line? Find the slope. What's the slope? No, slope is not e to the x. So this is where the study time helps. Not grinding problems, but study time when you understand what's going on. Someone might try to make an argument now, but we never did e to the x. Doesn't matter. I can put there tangent hyperbolic. You haven't even seen that function yet. The principle is the same. What you have to learn is that the derivative is a function which generates slopes of tangent lines. Therefore, you need the derivative. And how does it generate? Well, you're going to have an x in that function, and you will plug in the value given to you. So the tangent line in 3.1 and all other sections, including tangent planes in Calc 3 and so on, slope fields, differential equations, they're all the same all the time. The derivative is the function that generates slopes. You plug in x to find the slope. So The first step is always to figure out the derivative. In this case, it's the same. And then the derivative becomes tangent line when you plug in the value. These guys cancel, so your slope is 3. Now, you have the slope, you need a point. Obviously, your x-coordinate is ln 3, that's given to you. And the y-coordinate is always function computed at that value. So in our case, that's e to the x ln 3, so it stays the same. So it's ln 3, 3 for the point. Y equal mx plus b. Y is 3, m is 3, x is ln 3 plus b. B equals 3 minus 3 ln 3. And finally, slope of the tangent line is 3x plus 3 minus 3 ln 3. Make your peace that all of this is a number now. Yeah, you could go and get the decimals. No one cares. All right? It's a number. So there's your y equal mx plus b. You can see b. You computed it. Trig is going to have more interesting things there, including pi and stuff. Procedure for tangent line will never change. What's going to change is the way you find the derivative. So tangent line problem remains the same in every section. What's different from section to section is it the basic derivative or product rule, quotient rule, chain rule, implicit differentiation, logarithmic differentiation, all of these other ways to take the derivative that we are going to learn. So it's like a block over here. Insert whatever method is needed to find the derivative. The rest of the problem, once you have the derivative, plug x and find b. That stays unchanged section to section. This problem will be on your next exam 100%, on your following exam 100%, and on your final exam 100%. Because finding the tangent line is the central problem of Calculus 1. Calculus 1 deals mainly with derivatives. So I would say, 30% on 20% limits, 20% integrals, and 60% differentiation. Out of those 60%, tangent line is the line that measures the change. And that's 60% of our course. This problem must be included on every test, 2, 3, and the final. You have to know how to find tangent line at any point in time, because that's what Calc 1 is most about. Shall we do another tangent line or finish off the lecture with the higher derivatives and be done? Another tangent line. See, you guys are intelligent. I like that.
Something with like trig functions?
We did not cover the trig derivatives yet. We are going to cover that in, I believe, 3.5 or 3.6. And then, as soon as I say the derivative of tangent is secant squared, the next problem, find the derivative for tangent x. Find the slope of tangent line function tangent, right? And then you will be doing that. So we're going to see this problem in every lecture in chapter 3, using whatever method of derivatives we're learning. Right now, still doing this stuff. So here we go. TL question mark. That's going to be the trademark question, right? What's the tangent line? And then I need to give you the function, and I need to give you the point. So a function is x cubed minus 4x squared plus 2x minus 1. And the value is 2. You know what to do. The problem.
plugging in the value of x.
Yeah, so you have 2 measure x, and then so you get the derivative, and 2x.
But look, when I'm solving y equal mx plus b, I need a point, x comma y.
Yeah.
To get the point y, I plug 2 in here to get the y. So I plug this one into m to get the slope, and I plug into this one to get the y. So I have m, x, and y to find b, because I have 4 variables there, right? X, y. Yes. Original gives me y, because y is f of x. And the derivative is m. So I have those 2 plus x plus b, and then go.
That's all.
Everything makes sense?
No, yeah.
Yes, because it's calculus. The beauty of this stuff. It makes sense properly.
I'm surprised, but that's right.
Oh, yeah.
Well, I thought it was going to go with 40.
What's something to okay? It's only first of that. This is correct. Yes. You have finished okay, so say your grade is 45, and someone's grade is 95. They don't matter, right? You understand that those 2 students have 5 points apart? Yeah, they're standard 0 because the derivative of constant is 0. So 45 on this exam and 95 on this exam are 5 points apart for the overall grade.
Yes,
This is a different kind of answer. There's a huge gap, a huge jump, an adjustment from algebra to PreCalc, and then there is another jump and adjustment from PreCalc to calculus. Students probably are not used to learn more. It's like, okay, this is multiple, maybe I can squeeze through. Most likely not. You understand this concept, you say, okay, tangent line. All right, so the derivative is generating all the slopes. So I plug x in there, and then I got the slope. Okay, so I have to have the derivative. There's a reason why you take it. And then, oh, I need y. How do I find y? I plug x into the original equation. Right? So, you know, you look for the missing pieces of the puzzle, you put them all together, and there it is.
Is anyone going to help me with the derivative over here? I'm kind of rusty. 3x squared, okay. Minus 8x. Plus 2, nice. All right. See this x to the 1. And 1 minus 1 is 0. X to the 0 is 1, right? And then what's the derivative of negative 1 over here? 0, good. How much is m? We calculate m when we plug in 2 into the derivative. So what do we get? Negative 2? Let me write the steps. So 3 times 2 squared minus 8 times 2 plus 2. And we get negative 2. Do we all have negative 2? No? Get it. Get it quickly. So we have 12 minus 16 is negative 4 plus 2 is negative 2. Get it quickly if you don't have it. All right, so I have m, I have x, I need y. Where do I find y? Right, to plug stuff into y equal mx plus b. Where do I find y? Nice. Plug 2 in the original equation because y is equal to f of x. So if you plug in 2 into original equation, you get y. Great. So plug in 2. So y is equal to f of 2, which is 8 It's 3? Negative 5? You guys want to take it outside? What is it? 3 or negative 5? Negative 5? See? Girls are joining in. That means discussion stops, right? It is negative 5. Good. So now we have y is negative 5, m is negative 2, x is 2 plus b. So b is negative 1. Y equals negative 2x minus 1. There's the answer. Ta-da!
So a constant within a derivative wouldn't be 0.
No.
Okay. So it's
When
only
you
the
take
constant-
derivative of the constant is 0.
Okay, so it's when you get
Yeah.
the constant before you take the actual, you get the actual derivative. So something like in this is, we got the 2.
Yes.
That one holds when the 1 wouldn't.
Well, this, yes. So this 2 came from here. And I'm going to kill it now.
Unfortunately.
Yes. Because if the first derivative has the constant, that constant is going to die in the second derivative because you're taking the derivative of the first derivative. So now the last part of this lecture is to talk about higher order derivatives. I start with y equal f of x, and then I can take the first derivative, which is f prime of x. Second derivative, which is f double prime of x. And then third, which is f triple prime. And then fourth, notation is changing. All the way to the nth derivative, which is this. How many derivatives can I take? As many as I need for whatever application we are observing. I will just tell you this right now, but we are going to have a lecture on this eventually. If you're talking miles per hour, which is a speed, that is actually the derivative of the position function. So, position function is the function, and that's going to be the path, all right? And then you take the derivative of that, which is the first derivative. So you have the function, you take the first derivative, and you have velocity. You take the second derivative, you get acceleration. You take the third derivative, you get jerk. So physical concepts are related to these things. And we use them to model the world. So in application, I've never seen past the fourth derivative. But, as stated over here, you can go as far as you want. So now, if I start with the function f of x equals 4x cubed minus 2x squared plus 8x minus 9, and I take the first derivative, I go with 12x squared minus 4x plus 8. And the 9 dies because the derivative of the constant term is 0. Now, I want to go and find the second derivative, which is the first derivative of the first derivative. So I will take derivative here, the first derivative, and I get 24x minus 4. If you try to do this with negative exponents, they go more negative. They never go to 0. So if you start with a function 1 over x, the derivative is negative 2 x squared on the bottom. And then the second derivative is positive 4 x cubed, and so on. So you see that in this case, we are not going to end up with 0. What's the 197th derivative of e to the x? I know. Isn't that awesome? Right? What is 197th derivative of e to the x? Answer in the next class. E to the x. You will also find that trig also never dies out. You will see that derivative of sine is cosine, derivative of cosine is negative sine, and they're going to oscillate like that between sine and cosine. So when I ask you what is the 197th derivative of sine, we're going to find a very cool way to, that's correct actually. So we're going to figure things out. All right. So now what's going on? I have to take long. Well, it's not break. I have to go do some other work. You guys will work on lab. After that, we'll have another lecture. So take a few seconds to I don't know. Enjoy life. No, you enjoyed life now. So just be miserable for like 5 seconds and then we'll restart the lecture. Give me 1 second. I'll just need to see because the stream didn't stop and the program crashed. So it's still streaming. I'm trying to shut it off. I'll be right with you. Give me 1 second. I think I have to shut it from the console. Why is this?